Since ChatGPT emerged and spotlighted artificial intelligence, it has evolved from a theoretical concept to a technology people use daily. The medical sector is a particular industry that is looking to embrace AI. Last video, we saw how Google has taken great strides in medicine by introducing Articulate Medical Intelligence Explorer, or AMIE for short. MIT researchers are on their way to receive the baton from Google. With the help of AI, they have discovered a new set of antibiotics. Today, we will discuss these discoveries and how they may lead to saving the lives of thousands of Americans every year. Please remember to like, subscribe, and turn on notifications. Let's begin. If you don't already know, deep learning is a product of machine learning and artificial intelligence. With deep learning, computers can process data as humans do, but at an unfathomable scale, and carry out complex tasks more accurately. Using this technology, MIT researchers have discovered substances that can fight the methicillin-resistant version of the Staphylococcus aureus bacterium, known in short form as MRSA. The researchers discovered that the compounds could destroy MRSA grown in a lab dish and 2 mouse models of the infection. The antibiotics were also found to have low toxicity and likely to be compatible with humans, making them excellent drug prospects. Felix Wong, a postdoctoral researcher at IMES and the Broad Institute of MIT and Harvard, and Erica Zheng, a former Harvard Medical School graduate student, led the study. This research is part of MIT's Antibiotics AI project. The program aims to create antibiotics to combat 7 of the world's most dangerous bacteria over 7 years. The strains of bacteria are Acinetobacter baumannii, Escherichia coli, Klebsiella pneumoniae, Mycobacterium tuberculosis, Neisseria gonorrhoeae, Pseudomonas aeruginosa, and Staphylococcus aureus. Over the next 30 years, the project team's primary focus will be on developing therapies for superbugs, which have the highest potential to infect humans and cause fatalities. The Antibiotics AI project seeks to combat these diseases, to prevent millions of deaths, significantly increase humanity's capacity to develop innovative antibiotics, and efficiently treat existing and newly emerging resistant infections. What is so peculiar and perhaps a critical aspect of the latest study is that the researchers figured out the types of data the deep learning system used to predict the potency of the developed antibiotics. With this information, they can create other new drugs that might even be more potent. A professor at MIT's Institute for Medical Engineering and Science, James Collins, commented on how he and the researchers were able to take note of the data the deep learning model required to make the antibiotics. He said, "The insight here was that we could see what the models were learning to make their predictions that certain molecules would have good antibiotic properties. Our work provides a framework that is time-efficient, resource-efficient, and methodically insightful from a chemical structure standpoint, in ways that we haven't had to date." The Termir professor and his teammates at the Abdul Latif Jameel Clinic for Machine Learning in Health at MIT have experimented with deep learning in an attempt to create new antibiotics. One of their noteworthy accomplishments is the creation of antibiotics against Acinetobacter baumannii, and they have similarly developed antibiotics that work against other drug-resistant bacteria. Methicillin-resistant Staphylococcus aureus, commonly called MRSA, is a staph bacteria resistant to several antibiotics commonly utilized for fighting these infections. It is usually found in people who have stayed in senior housing facilities, dialysis clinics, and other healthcare institutions. In such circumstances, it is called healthcare-associated MRSA. These MRSA infections linked to healthcare settings are typically related to invasive medical procedures or devices, including artificial joints, intravenous tubing, and surgeries. Healthcare personnel who touch patients with unclean hands or come into contact with contaminated surfaces may spread HAMRSA. Healthy individuals contract a different kind of infection in the larger population. Community-associated or CAMRSA strains sometimes start as excruciating skin boils. Skin-to-skin contact is the usual method of transmission. Individuals who work in childcare, are living in crowded housing, or are high school wrestlers are examples of vulnerable groups. More than 80,000 Americans contract MRSA each year, and the bacteria frequently results in pneumonia or skin infections. Severe cases may result in sepsis, a blood infection that can be lethal. Collins and his fellow researchers have spent years developing prospective solutions to drug-resistant bacteria. First, they employed deep learning systems that detect chemical patterns related to antimicrobial properties. After combing through millions of additional compounds, the models then estimate which have potent antibacterial qualities. While their studies have been productive, the researchers encountered a hurdle, and that is that these deep learning models were like black boxes. There was no means to identify what properties the models had used in their projections. This information would have allowed the scientists to spot or develop more antibiotics. Felix Wong shared that the goal of the new study was to unravel the black box. He stated, "These models consist of very large numbers of calculations that mimic neural connections, and no one really knows what's going on underneath the hood." For the research to develop antibiotics against MRSA, Wong and the other researchers used more datasets to construct a deep learning model. About 39,000 compounds were tested for antibiotic activity against MRSA to produce the training data, which was then fed into the model along with details about the chemical compositions of the compounds. According to Wong, almost any molecule can be represented as a chemical structure, and anyone can inform the model that the structure is antimicrobial. Several examples of this sort are used to train the model. When a new molecule with an unusual bonding and atom configuration is added to the model, it can predict whether the compound would have antibacterial properties. Using the Monte Carlo tree search, the researchers could get a bearing on how the model was making its estimations. This tree search algorithm has been previously deployed to gain more insights into other deep learning systems. It allows such models to produce a prediction for the molecule's substructures that are most likely responsible for the antibacterial activity of each molecule. The researchers created 3 additional deep learning models to improve the selection of possible medications. These models were developed to predict a compound's toxicity to 3 different types of human cells. By combining these hypotheses with evaluations of antimicrobial effectiveness, the scientists discovered substances that might eradicate microorganisms while posing the least risk to human health. The researchers used a series of models to screen around 12 million commercially available chemicals. Based on chemical substructures in the molecules, the models identified compounds from 5 classes predicted to have anti-MRSA properties. The scientists then acquired over 280 different chemicals to test against MRSA grown in a lab dish. 2 potential antibiotic candidates from the same class were found thanks to this technique. In studies on 2 mouse models for MRSA skin infection and MRSA systemic infection, every drug showed an incredible 10-fold decrease in the MRSA population. According to the results of the conducted studies, these chemicals appear to kill bacteria by interfering with their capacity to maintain an electrochemical gradient across their cell membranes. This gradient is critical for several vital cell processes, including the synthesis of ATP, which is needed for energy storage. While MRSA is a gram-positive bacterium with thicker cell walls, halicin, a different antibiotic candidate initially identified by Collins' team in 2020, works by a similar mechanism and is specific to gram-negative bacteria with thinner cell walls. The research findings have been sent to Fair Bio, a non-profit organization that Collins and Associates founded under the Antibiotics AI project. The organization plans to thoroughly investigate these substances' chemical characteristics and possible medical uses. Meanwhile, Collins' group is hard at work, developing more potential drugs motivated by the study's findings. Additionally, the lab is using the models to find chemicals that can eradicate different strains of bacteria. AI is helping humanity take the next steps in our fight to stop bacterial-related infections and deaths. If completely successful, the Antibiotics AI project will prove to be a formidable ally in the healthcare industry.